So, chapter 6. So what are we going to do today? I'm going to start with a little review of testing in Rust in general, and then we'll move on to what the book has to say. So, it's I'm going to review because this book club started with the book, or the Rust programming language, which has a chapter on testing. And a couple of years ago, Christoph led this session on that and covered it really well. So he outlined 4 parts, or 4 different kinds of Rust testing: unit testing, doc testing, integration testing, and benchmark testing, and covered the first 3 pretty thoroughly, and mentioned the 4th one and said it was outside the scope of this book. So how does testing go in in Rust? So So if we start a new project with cargo, it generates hello world, which is fun and amusing, and it's nice to get a binary that you can just run straight away, and it prints hello world. If we start a new library instead, then if we cargo new a library, instead of getting cargo world, we get a little function and a test for it, which is super cool. But the only thing that could be cooler than this is if it produced a failing test for you TDD folks or whatever. But it's a passing test. So, and we see that a test is just a function, and we call our function above, and then we make some assertion about the result that we get. And then this macro does most of the heavy lifting that turns this ordinary function into a test. But it doesn't stop there. It's idiomatic Rust to put our tests in a separate module, and then this macro, this whole thing, there we go, that macro changes the compilation context to testing. And because this is a separate module, we have to sort of use the place we are, and then this is public. So then instead of cargo run, we can cargo test, and here's our function, and it passes. Now here's the call to our function, and it passes. And then we see that cargo test also looks for doc tests. It didn't find any, but it looks. So more on that in a minute. So we see that this sort of built-in testing framework for Rust is all based on these macros. Test does most of the heavy lifting, and the compilation context change does the rest. And then we have assert and friends, which are more macros for sort of doing the actual each individual test assertion. And then there's more things we could do. Christoph mentioned in the first book, the ignore. We can write a test that instead of just returning a value, panics, and then we have a should panic that makes it not panic in our test, but pass as a should panic, and so forth. The most recent version of Rust has a diagnostic attribute, stabilized. This isn't testing per se, but it seems testing adjacent to me, so I included it just because it just happened the other day. There's also a bench attribute, which is not stabilized yet, but it's sort of fits in as well. And then I just wanted to mention, just because I love programming exercises so much, there's this exercism site, which is a programming exercise site, which is test-based. So in addition to sort of a description of the puzzle that you're supposed to solve, there's a test suite for it. This started out years ago in Ruby, and it was Ruby only at first, but then they expanded out, and now it includes lots of different languages, and it has, including Rust. And it uses whatever the sort of unit testing framework is for your language. So in the case of Rust, we have it easy. It's sort of obvious what to do. Some languages have more than one testing framework, and you have to, they picked one and you have to live with it if that's not the one you prefer or whatever. But in our case, it's almost certainly this is the way we do it anyway. Typically, there's a whole suite of tests, and the first one will be active, and all the subsequent ones will be marked ignore. And then you can sort of go through in a TDD way and remove the ignore from one test at a time as you go through. Or if you're bold, you can just solve the whole problem. And then, again, Christoph mentioned this in his talk, that you can give it this include ignored flag, and it'll run through all the tests, whether they're ignored or not. So that's fun. All right, so what does our book say? Oh, the book we're currently doing. So here's our author at Rust Nation, just a couple of months ago, still talking about testing in 2024. He gave a talk on impeccable Rust. So there's a number of aspects to it, what he calls impeccable Rust. One of those was testing. So I just sort of did a screen grab on that slide. So forget about impeccable Rust for now. Let's go back to Rust for Rustaceans. What does that say? So there's 3 parts to this chapter, or really only 2 parts. The third part is a summary. The first part has some subparts. So Rust testing mechanisms. We talk about the test harness, this config test macro, section on test-only APIs, bookkeeping for test assertions, and a section on doc tests. And then the second section, additional testing tools, also has subsections, some of which have their own subsections. We're going to talk about linting, test generation, which includes fuzzing and property-based testing and some other things, but those are the only things talked about in the book. Test augmentation, and a few different ways of performance testing. And then there's a summary section, which is really just a paragraph, but it has its own section. Okay, Rust testing mechanisms. So first, the test harness. Let's go back to that little adder that's generated by cargo. And we can run cargo expand on it, and it sort of shows us what's really going on. But if we cargo expand lib tests, then it expands some more. And so here's the sort of first part. And then if we also expand the tests, it expands really quite a lot. And this is what I mean, that test macro really is doing quite a lot. Here's our test function, and it's almost unrecognizable. But really what I wanted to point out was this. So the sort of heart of this test is it generates a main for you, right? Because this is just a library. How does it run when you cargo test? Well, cargo test, the test harness includes putting a main around everything. So here's our main function, and here we are calling our test function, and just the one call in this case. But it all starts with this generated main. So in Rust for Rustaceans, it points out this is just the default behavior. This is a default test harness called libtest. If there's anything it does that we don't want, then we're welcome to write our own test harness. We don't have to sort of live with the generated one. That's just the default behavior. So we would have to turn it off, and we can do that in the TOML. And if you just say you don't want a test harness, then it complains that, well, then now you need a name. So you give it a name, and then it complains, well, now you need a path. So then you give it that. So you need all 3 of these things to actually get access to not getting the default test harness. And if you do that, John points out you want to be aware of some of the many things that libtest does for us, you've also turned off all of those things. So, and again, Christoph mentioned this, that there's this no capture and help switch and all these things that you might pass arguments, and those are interpreted by libtest. Well, if you need any of that behavior in your test harness, your custom test harness, you're going to have to do that. You've turned those are not available. Those are, you know, turning off the default libtest turns off that behavior as well. So you have to re-implement some things if you need them. So why might you want to do that? And the book says it's mostly benchmarking. The whole test harness features might get in the way of benchmarking is hard enough anyway, because it's just hard to do. It's hard to measure the right things and not measure the wrong things. So getting the most stuff out of your way is good. But in addition to benchmarking, fuzzing and model checking, he mentions, you might not want the use libtest, or more generally, sort of anything that requires a bunch of global setup, like if you're targeting WebAssembly or something, you might not want to target the default libtest. All right, next section was on this config test thing, which is, as Kira mentioned last time, a compilation context. So Cargo does a number of things when you do cargo tests, but ultimately it ends up calling the Rust compiler, and it does so with this -- test flag. So that's what's going on there. And then there's this odd sort of sidebar on mocking, and he talks about mocks and fakes. Because if you're testing something like connecting to a database or connecting to a network service or something, you probably don't want to do that as part of your test. You don't want your tests to be too slow, and you don't want your tests to be too fragile. You don't want to start failing tests sort of for the wrong reasons. So in those cases, we often use fake data or mocks. And in Rust, we generally do this with the generics system. But if we aren't already using generics or don't want to for some reason, then we might end up with a dedicated struct that we can then enable with this config test thing, or configure our own feature just for the testing our mocks. And I say it's an odd little sidebar because it takes up almost a whole page, and yet the conclusion is that we haven't really figured out the best way to do this in Rust yet. As a community, we're still working on this. We don't have a standard approach. There's crates to help you out. Maybe mockall's the most popular one, but it's on the one hand, he claims that mocking is essential or something like that. On the other hand, we haven't quite standardized it yet. So there it is. So the next piece is test-only API. So we have this machinery that allows us to make testing code different from the regular code. Why would we want to do that? Well, we might want to include code that we only need for the testing. And so his big example is the hash brown crate. And so this code appears on page 89. And well, I guess I'll go through it first, and then I'll go back and talk about my problems with page 89. But so the idea here is this hash map M has a table method, which is private, but we can see it if we're writing tests in the hash brown crate. We can see the private table method. However, what that returns is a raw table, which is in a separate module. And then buckets is a private method, which we can't see because it's a separate module. So yeah, so that's what we just talked about here. So we can see the M table if we're testing hash brown, but we can't see the buckets in the raw table module. So the solution, or a solution, is to implement this buckets method for raw table. And the buckets method, all it does is access that private attribute and return this slice of bucket. And then for the test, we change to calling this buckets method instead of the buckets private attribute. And then the rest is the same. So that's all well and good. And I've read this book a couple of times. I've read it when I first bought it, when it first came out. And then I read it again when we started this book club. And I didn't actually try this code out until I was preparing this talk. And I couldn't get it to work. So I don't know if I have the wrong hash brown crate or what, but the hash brown crate I found does not have a buckets thing. It has already a buckets method, and moreover, it doesn't return a slice of bucket. It returns sort of the number of full buckets. So it sort of does this whole count already, right? Because this is getting back a slice. This example implies it's getting back a slice of buckets, which we can iterate over, filter, and then moreover, this bucket thing has a is full method, which presumably tells you if the bucket is full or not, and then we're just counting them. Oops, that's going on to the next thing. So this all is fine, except the hash brown crate I found does not work this way. So I struggled with this for a good long time, and I created a different example to sort of make it all work with the hash brown I found. But then I decided I would just go over the code in the book as if it worked, and it's fine. The point is valid, and that is we're going to replace this buckets private attribute with this buckets method that we can see and use as part of our tests. And the real point is it's only for testing, so that we're labeling. We've made it public, so that's the real point. We're sort of created access to this attribute. We've made it public, and only in the testing compilation context. All right. So another reason we might want things only for testing is data. So, and the example in the book is if we're writing a buffered write, we might want to keep track of how many times we actually fill our buffer and have to call the write. So we create this field, and we'll create this field only in testing context. And then we'll increment that field every time the buffer is full, but only in testing context. So that's sort of data we don't need, and presumably it would slow us down or something, or make the code larger unnecessarily. And we only need it for testing. We don't need it for production. So we only have the data for production. We only manipulate the data. I mean, we only have the data for testing, and we only manipulate the data for testing. All right. And next section is doctests. So if we're writing a function, any function, we should be writing a docstring for it, right? A docstring is just the same as a comment. That would be a comment, but we put another slash on here, and we get a docstring. So in addition to commenting our function, we doctest will RustDoc will handle this and give us our documentation out of it as well. And we can put any markdown we like in a doc string, including these triple backticks, which sort of typesets it or whatever, marks all of this as Rust code. But moreover, not only is it treated as marked down as Rust code, but it's run as a doc test. So it becomes a test for our documentation. And again, Christoph mentioned this is an integration style test. We can't have private fields or methods. And we're not sort of compiling that with tests on main. Each test gets its own main. So we saw this line here where we actually have to use our own library that we're testing, or our own method that we're testing. But if we didn't want to show this as part of the doc string, that's what this is all about. So this will sort of include this, this use mylib frobnify, which is necessary, but the Octothorpe here will say, well, we don't actually want to display this line, so hand it to the compiler, but don't show it to the person reading the doc. And then there's a second doc test in the same example, which says, so it's going to write a main for us. And it doesn't have to just be a simple main. We can actually sort of coach it into what the return value has to be. And that's what this last line here is doing. It's sort of forcing it to be return a result instead of just unit or crash. Panic like a regular test. So that's necessary because this parse is going to return one kind of result, and then frobnify is going to return a different kind of result. So we're coaching it to let the anyhow magic sort of fix those both up for us and return the sort of dynamic result that we need. What the book doesn't say is that we have to include anyhow to make that all work. And we don't have to include it in our dependency section. We could just put it in the dev dependency section. And we could even use Rust block comments and block out entire sections. And he warns us to use this very sparingly, because unlike this, which is just sort of hiding away one thing, this is potentially hiding away tons of stuff. And we have to, it's sort of that much more dangerous to hide away too much stuff at once. And all these examples, all three of these doc tests needed this line because they're each their own separate thing. They each get their own main. So they each need this. But only one of the three had it in the book. So that might be a little confusing. And then this one needs this also for this question mark, and it didn't have it either. So I found it ironic that he's warning us to not hide too many lines that you need to understand the code that you're looking at, when he hid too many lines, I think, from page 91. Oh, and then so if you want to include attributes in your tests, how do you do that for doc tests? And you just stick them after the triple backticks. And so here's an example that it's supposed to not compile, and it does, so that test will pass instead of fail. All right, next section, additional testing tools. Linting. So there's the usual Rust linter is called Clippy, and it has both correctness lints and other kinds of lints. Additionally, there's more lints in the Rust compiler itself. Those show up as warnings. We don't really have correctness lints because we call those errors. And we can see a list of all those by invoking rustcw help. And that's not even all of them. There are more Rust compiler warnings that we can turn on. They're off by default. The 2018 edition came with all kinds of changes in idioms, and you can sort of have the compiler check those for you. And if you have public methods or whatever, and they don't have doc strings, you can ask for the compiler to find those for you with the missing docs. And public but no debug, and you can look for that with missing debug implementations. And we can enable those in our code like that. And we can even have our code fail to compile instead of just give a warning by saying deny instead of warn. Test generation. So there's sort of two kinds of test generation mentioned in the book, fuzzing and property-based testing. And for fuzzing, there's this cargo fuzz, and that accesses the fuzzer, and LLVM sort of has its own libfuzzer. And cargo fuzz just, I guess cargo fuzz is a framework that can use any fuzzer, but right now the only one it uses is libfuzzer. And that's, of course, a sort of framework for throwing random data at your program and seeing if it crashes. Property-based testing is a sort of more organized version of that same principle. And there's at least two different crates to help with property-based testing, prop test and quick check. Quick check is the historically correct name for this sort of thing. It comes from these two guys who, working in Haskell about 25 years ago, came up with this quick check library for doing this property-based testing. Instead of writing out every unit test, a quick check would generate thousands of tests and throw them all at and so instead of writing unit tests, you write quick check tests, which write your unit tests for you, thousands of them. But the really cool part about quick check, I think, is sort of part two. If it finds some data that causes your test to fail, it doesn't just throw the random garbage back at you and say, this random garbage makes your test fail or makes your code fail. It instead starts sort of part two of the algorithm is shrinking. It keeps making the input that it found smaller and smaller until it stops failing. And then it backs up one and gives you the smallest version of the data that made your code fail. And to me, the shrinking algorithm is the cool part of quick check, not the test generation part. So here's an example using prop test. Prop test is an example of quick check too. It's just a different name. And so the Paul cipher comes from this puzzle that it was at the end of this this newsletter that I was looking at a couple of years ago. And way down the bottom is the closure challenge. And this week's challenge was the Paul cipher, which is this little simple little cipher, and it has your task is to write an encoder and decoder for this simple little cipher. And you can see here there's a bunch of examples of encode and a bunch of examples of decode. And so this is a closure thing, but I did it in Rust. And here's what it looks like using prop test in Rust. And I wanted to show this example because it's a perfect example of how to sort of use property-based testing. Because often the hardest part of property-based testing is thinking up a property, right? You have to think differently to write a property-based test. But something like this, that you have both an encode and a decode, or do a thing and undo a thing in general, is sort of a free property automatically. If you're doing the do the thing and undo the thing, if you're writing both of those, then you get a free property that you can test with a property test framework. Because if you take your thing, you take your randomly generated data, encode it, and then decode it, you should get your thing back again, or something close enough. In the case of the Paul cipher, it's not quite S, but the uppercase version of S that we should expect back. So the hard part of property-based testing is sort of we get for free when we have this kind of situation. In other contexts, thinking up a property is the hard part. Whatever. So this generates a random S, and then encodes it and decodes it, and make sure we get the same thing back. When we're doing property-based testing in practice, we don't stop there. If prop test finds a failure for us, then what we ought to do is take that failure, fix the bug, of course, but then encode that in a plain old unit test in our regular test framework, right? In our regular unit test suite. So this is what I've done here. These are those examples of encode in the in that newsletter, and I've just sort of added this one because when I ran those property tests, it found this, and you can see it shrank the input example all the way down to 1 character. So that was a pretty successful shrink. But rather than rely on prop test to find this again, we just encode it as a normal unit test, and then we don't have to worry about it anymore. So that to me is the way to use prop test. And in the book, he says this quote about fuzzing in some sense is a degenerate version of property-based testing, where the property we're testing is it doesn't crash. So that's kind of an interesting way of looking at it, I thought. And it's not limited to a single function call. This is another one of those weird little, not weird little, but this was in a little box like a sidebar, like the mocking thing. It said not limited to a function call. We can do a whole sequences of functions. And minimizers, I think this is, he didn't say what he meant by minimizers, but I think this is the shrinking step 2 of quick check. That's what he means by minimizers here. Even if you had a whole sequence of operations, the quick check or prop test minimizer will sort of still find you the smallest thing you can test on. All right, the next part is test augmentation. If conditions that cause failure are rare enough, then this can be problems. This can cause real problems for testing. And some of the most difficult things to test for are things that only show up if they're on different threads, or undefined behavior in unsafe code. We could try, if things are just rare, we could try repeating it maybe 1,000 or 1,000,000 times and repeat it enough and it'll show up eventually, but maybe it won't. So it can be very frustrating testing in these situations. So there's a couple of other things we can do instead. MIRI is an interpreter for MIR. That's what MIRI stands for, mid-level intermediate representation. So the Rust compiler is multi-stage, and we sort of lower the code at each stage. And one of the intermediate stages is the MIR stage. And from there, if we interpret things in there, we can find problems that we couldn't find at higher or lower levels. So that's what MIRI is all about. And then the book also talks about this thing called Loom, which is from the C world. And the name Loom is supposed to evoke interleaving threads. So this is a framework for helping us find problems that only show up in certain threading situations. So it will do things like, if you have two threads, it'll arrange for thread A to finish first and then thread B, and also for thread B to finish first and then thread A, and run your code under both and things like that. MIRI still runs under nightly, but if you have nightly, you can add it as a component like this, and then you can MIRI test or MIRI run your binary or library, and it'll find things that you won't find without MIRI. So here's the example from the book. I think he calls this wildly unsafe code, where we have two references to the same data. And if we run this, it seems to run fine. There's no problem. Both references show us 42, and it's not a problem. But if we run this under MIRI, we get problems. So it says this is, and if you understand more than I do about this sort of thing, then this is apparently a very good error message that tells you exactly what the problem is. So MIRI did a great job. I don't have an example of the Loom thing. So on to performance testing. So there's sort of three separate parts here. We don't want our performance to vary. If we make some change and our code is much slower, or indeed if our code is much faster, then maybe something bad happens. If we don't know why our code sped up or slowed down, we'd sort of like to know why. And then performance testing in the face of compiler optimizations is problematic. And then we have to also be careful of I/O overhead. So there's a couple of different things for performance variance. There's this HDR histogram library from the Java world, which has a port for Rust. So that's a high dynamic range histogram. So that's sort of a more fine-grained version of sort of keeping the history of your program. So you can really tell in a more useful way that your code is faster or slower than it was yesterday. And then Criterion is this sort of benchmarking framework. And I think things are going towards that for a standard. I think when Cargo Bench is a standardized thing, it's going to look like Criterion if it isn't actually Criterion or whatever. And finally, compiler optimizations. So there's this online tool called Compiler Explorer, and it's this website called Godbolt, which is such a great name that everyone just calls it Godbolt, and most people don't even know the name Compiler Explorer. Interestingly enough, Godbolt is just the guy's real name. That's just the name of his website. But I think it's funny that nobody actually calls it Compiler Explorer. the book mentions, I mean, you can also do this at home. You don't need to go online to look at the assembly code for your Rust code. You can do this right in the comfort of your own home. Cargo ASM is deprecated in favor of something called cargo show ASM, but after you install it, you don't need to know that anymore because the command is the same. Also, this black box thing, which I think used to just be part of Criterion, is standardized now, stabilized now. So we'll see that in a minute. So yeah, instead of cargo ASM, we want cargo show ASM. And so here's a little thing we want to benchmark. We're sort of starting a timer, pushing some things onto a vector, and then seeing how much time it took. And if we look at the code for that, it's not doing as much as we would like. So there's this black box thing, which doesn't really do anything, but it sort of tricks the compiler into thinking that we might have. It's like, and the name black box kind of evokes that. It's like we're sort of pulled a curtain in front of the compiler and said, you cannot assume that nothing happened. Something might have happened to VS in this routine. So you cannot optimize this code away anymore. And so then now if we expand the assembly, we get a lot more things happening, and our pushes are actually happening. And then there's I/O overhead. So this is just something to be careful of, and it's just an example, a great example, I think, of the benchmarking is hard. So the way the book puts it, I think, is it's like, what do you suppose this function, or what do you suppose this is testing? So again, we start our timer, and then we do something a million times, and then we see how much time elapsed. Well, print line is actually a lot of work. So unless your function is very slow, you're not really testing how long it takes to run your function a million times. You're testing how long it takes to print line a million times. So we have to take pains not to do things like stick I/O in the code that we're testing, because it has a tendency to sort of dominate. And then we can't actually test the code that we want to test. All right, that's everything in chapter 6. There's just one little paragraph at the end that summarizes it. We looked at Rust built-in testing capabilities and some testing facilities and techniques. And then he goes on to say that this is the last sort of higher level chapter. So starting next time with chapter 7, we should be seeing a lot more Rust code with chapter 7 and the rest of the book. So that's all I had.
Awesome. Thanks, Tim. That was great. So we'll open it up for general questions and chat now, especially for folks who read the chapter. That was a brilliant summary, and lots of like extra stuff in there that's not in the book as well, which is always great. I had a request for your slides, but Johan spotted the link, so that is now shared in.
Yeah, and I didn't follow all of the links in the slides, but all of those things that are sort of gold colored should be links to relevant places. So if you are going through the slides, you can follow some of those links if you get lost or have questions.
So mainly thank yous, and many questions in the chat just yet. I think like testing such a
The Rust Nation talk that I referenced, he talked about mutation testing in there, which is not in the book. And I almost included it just because it's so interesting, but I decided not to because it's not in the book, and this is a book club. But there's this whole notion, sort of related to, I think, to test generation, is mutation testing. I don't know how many people are familiar with that, but that and there's a cargo mutant, or cargo mutants plural, I think, which you can look at. And then the idea with mutation testing is you take your code and you introduce a bug. You mutate your code in such a way that it has a bug, and then you run your test suite and see if your tests still pass with the introduction of a bug, then essentially you have a bug in your tests. Your tests are not complete, or your tests are not finding a bug that you've introduced. So it's kind of like test generation, not really in reverse, but different or whatever. It's a neat idea. I've heard about that idea in the context of other languages before, but until that talk at Rust Nation, I just watched the video. I didn't go to Rust Nation, but until that talk, I didn't know about cargo mutants or how to do that in Rust. What book am I referring to? Oh, you figured that out. Okay. I'm just looking at the comments for the first time. So. Carlo, yes, Till Oylensheepgul is exactly right. It's just a phonetic spelling of that. The first time I needed, I wanted an Oylensheepgul reference. The name spelled properly like that wasn't available, so I just spelled it out however I felt like it. And I've been using it ever since. That was like 20 years ago at least.
There's no other questions right now. I'll put out just a request for speakers. So we're obviously doing the book club at the minute. We've got someone for chapter after next. I'll cover the next chapter unless anyone wants to volunteer to cover macros, in which case I will always happily give it up. But yeah, there's also quite a few chapters still to come. So take a look and see if any are interesting to you. And if you're interested, then yeah, message Matt or myself, or just post in the group chat, or there's a Google link, like a Google Forms link that I'll drop in the Discord. That's a good point. I haven't put the Discord link in the chat. So we have a Discord that's, it's fairly quiet. We don't chat all the time, but we use it to like share when a meetup's happening, if we remember to, and just post stuff that's going on and links like this. So yeah, if anyone has the Discord link handy, then please drop it in the chat. If not, I'll grab it in a second and then drop it. Thanks, Matt. Perfect. Yeah, and we're currently trying to stick to the 2-week cadence, so I won't bother sharing the slide for it, but the next meetup will be this Wednesday in 2 weeks.